In November 2003, someone tried to put a backdoor inside the Linux kernel, not in a library, not in a user space daemon, inside the kernel itself, the code that runs every Linux server on Earth. It was 2 lines of C, it looked like a bug fix, and if it had shipped, every Linux box that called one specific system call in one specific way would have silently handed the caller root. It got caught, and today I want to walk you through how and what it tells us about the kind of attacks we still see on Linux right now. The story comes from Ed Felten over at Princeton Center for Information Technology Policy. He wrote it up in 2013, 10 years after it happened, but the original incident was November 5th, 2003. Back then, the Linux kernel was developed in a version control system called BitKeeper. BitKeeper was the source of truth, but because BitKeeper was commercial software at the time, and a lot of developers couldn't or wouldn't use it, the project also published a CVS mirror so anyone could read the tree. That mirror is where the attacker went. A developer named Larry McVoy, the guy who built BitKeeper, noticed something weird in the CVS copy. Every change in the CVS mirror was supposed to have a backlink, a little metadata pointer saying this commit corresponds to that BitKeeper change set. It was bookkeeping. Nobody really looked at it. This change had no backlink. It existed in CVS and nowhere else. This is the entire backdoor. 2 lines inside the wait for system call, the call a parent process makes to wait on a child. Read it the way a tired reviewer would read it at 11 p.m. on a Tuesday. It looks like the author added some input validations. You know, if somebody calls wait for with these 2 flags set and the current user's UID is 0, return an error, defensive coding, move on. Except look at the UID check. It's a single equal sign. In C, 1 equals sign is assignment, 2 equals signs is comparison. A single equals sign here doesn't check whether the user is root. It makes the user root and then returns true because the assignment succeeded. Any program that called wait for with that specific flag combination, gets you a combination that's normally invalid, would silently get its UID set to 0, root, game over. Here is the part that earns my professional respect, even though I hate it. The C compiler, GCC, normally warns when you do this. It has a specific warning for this exact pattern because it's almost always a typo. The attacker wrapped the expression in extra parentheses. That's the GCC convention for telling the compiler, yes, I meant to do that. Please be quiet. The warning never fires. The code compiles clean. This wasn't a clumsy slip. This was somebody who knew the kernel, knew C, knew GCC, and knew what code reviewers tend to skim past. So why did this fail? 2 reasons, and they're worth holding on to. Reason 1, the wrong repository. The attacker put it in the CVS mirror, not in BitKeeper. The official kernel was cut from BitKeeper. To get into BitKeeper, the change would have had to go through a real maintainer, a real review, a real signed off by chain. It never would have made it. Reason 2, a metadata mismatch. Every CVS commit was supposed to point back to a BitKeeper change set. This one didn't. Larry McVoy saw a commit with no backlink, pulled the thread, and the whole thing unraveled within hours. The attacker beat the technology. They wrote a backdoor a senior kernel reviewer might have missed. What got them was the process, a boring bookkeeping field nobody thought mattered. 3 takeaways. 1, the attacker only needed to flip a single character equals to double equals, and an entire planet of Linux servers would have had a silent root escalation built in. That is the threat model for supply chain attacks even today. Tiny diff, enormous blast radius. 2, it got caught by integrity checks on the source, not by anything running on a live machine. In 2003, that worked. In 2026, our attack surface is bigger than the kernel tree. It's container images, base images, build pipelines, dependency graphs, AI-generated patches. You cannot review every line in every package the way Larry McVoy reviewed that CVS commit. 3, the question is no longer just, did the code I shipped match the code I reviewed? It's also, is the code I shipped behaving the way it should be on the running machine? Because somewhere out there, somebody is trying the modern version of this trick right now, and they are not going to forget to include the backlink. This is exactly the gap Sandfly's security was built for. They are a Gula Tech Adventures portfolio company that does agentless Linux runtime threat detection. Hash-based file integrity monitoring would not have caught the 2003 backdoor even if it had shipped, because the kernel binary was officially signed by the distro. What catches a backdoor like that is noticing the behavior on the live host. An unprivileged process suddenly executing as root. A wait for call returning in a way it never should. A new SSH key in a place no human put it. A backdoor planted in a non-standard location. Sandfly looks for the post-exploit signal, the thing that happens after somebody flips the single character, and flags it on every Linux host you own without an agent on the box. If you run Linux at any scale, take a look at them. The 2003 attempt is a small story with a big lesson. The bad guys are not going to keep being sloppy about backlinks. The defense has to move from "did we review this" to "is this machine still telling the truth?" And hey, if you found this useful, please hit that like button and subscribe for more cyber history and the lessons that aged into the present tense. I'll see you in the next one.